Statistical tests. Statistical tests allow us to have a go, no-go decision. It is a type of inference. So far we have seen confidence intervals, we have seen control limits. Now we're going to look at how to set up an efficient statistical test. A test that helps us make decisions. Many times we are into decision-making process and we have to decide yes or no. We don't want a limit, we don't want an estimate with confidence, we just want yes or no, should I make this decision or not. So let's take an example. Let's say you are into wind turbine industry and you want to adapt a new technology, and your accounting folks in your team have told you that, hey, if the defect rates of this new technology is less than 40%, we should move to the new technology. So now you need to have a go, no-go decision. And how does statistic help you? Say, hey, should I go to that new technology or should I not go to that new technology? So decisions can be effectively done using a statistical test. So the way you start, step one, is to have a null hypothesis. A null hypothesis is basically status quo, preserving status quo, meaning we should not go to the new technology, the defect rates is higher than 40%. It's basically just preserving what it is today, right? And alternate hypothesis, HA, H0 is null hypothesis, which says defect rates greater than 40%. When defect rates greater than 40%, you stay where you are. You don't want to change and invest in the new technology. HA, alternate hypothesis, is when defects is less than 40%. So in that case, the first step is to identify what is your null hypothesis, which just supports where you are, and what is your alternate hypothesis. Once you do that, you'd have to find out like what is that alternate hypothesis is. It could be a left tail test, a right tail test, or a two tail test. A left tail test is when your alternate hypothesis has a less than or equal, less than sign. When it's less than sign, then it's a left tail test. So basically here, what we're saying is that we would reject the null when in this situation. This is when you reject the null. A right tail test is when your alternate hypothesis has a greater than symbol, right? If this was defects greater than, then you would have a right tail test. And this is where you would reject the null hypothesis. And when you have a not equal sign, your alternate hypothesis, like you say, hey, I would accept anything except 40% defect rate. Then it would be, you would reject the null here and you would reject the null here in those two limits. So this is just the three types of tests that you could run based on what is your alternate hypothesis. Step one is to define what your null hypothesis is and what's your alternate hypothesis. As soon as you define your alternate hypothesis, you have a clear picture as to what kind of test will you be running. And at what point would you reject the null hypothesis, right? Now there's this second concept that we need to be aware of. Type 1 and type 2 errors. We've had a brief introduction, but type 1 error is when you are active too aggressively. Meaning you're taking action when there's no action really needed. You're aggressive, too aggressive. Don't need to be that aggressive. But in type 2 error is when you're just too lazy, or you should be changing, you should be taking action, you should be detecting that there's a problem, but you don't detect that there is a problem. So there's a type 2 error. So in any of these situations, when we reject, we could be making mistakes, right? So let's look at this reality versus action taken. So the reality is that your null hypothesis says defects greater than 40%. Let's say this was the reality. Then for you to stay where you are, which is to accept the null hypothesis and reject the alternate hypothesis, is to be sane. Saying, hey, defects on the new technology is greater, I'm not going to do anything, right? But let's say you did a sample pilot test, and then you found out that, hey, the defect's actually smaller than 40%. But the reality is that defect's actually greater than 40%, so you then acted too aggressively, right? So you reject the null hypothesis, you're here. Let's say type 1 error. How would we draw type 1 error here? You got a sample that was in this area, but the reality was that it was actually here. So your sample did not represent the reality, and so you took your decision based on the sample's input. And so you rejected the null hypothesis. When you reject the null hypothesis, accept the alternate hypothesis, when in reality that was an error, then it is a type 1 error. Similarly, let's assume that alternate hypothesis is the reality. The reality is that the error is less than 40% in the new technology. And then the type 2 error happens when you fail to take action, right? So let's say you got a sample that was here, and so you said, hey, I shouldn't take action, but the reality was that it was here in this section where you should have rejected the null. So what you do, you accept the null hypothesis and you reject the alternate hypothesis. So you fail to take action because your sample was misleading, or your sample was not representative, or maybe it was not randomized. So when you fail to take action, that is type 2 error. So the reason why this context is important is because when we take actions based on these data points, there is a chance that we can have a type 1 error, there is a chance that we can have a type 2 error based on what our pilot study tells us. And there is a 50% chance that you would do the right thing of not acting, or you would do the right thing of not acting or acting, right? So step 1, create null hypothesis, alternate hypothesis, know what kind of tail tests you're going to be running as to when you would reject the null hypothesis. And all of this is actually just answering yes or no to reject or not to reject the null hypothesis. This doesn't talk anything about the alternate hypothesis. It just says you should reject the null or not reject the null. So that's an important step to keep in mind. So now let's take an example, a real life example. Let's say you run an experiment. So the best way is to run an experiment where you have a control group and a treatment group. You have old technology, new technology, and you try to check what the new technology output is and what the defect rate is, and you check with the old technology, and then you take samples from both of them. This kind of experimentation where you test the new and test the old and take samples from both of them is called experimentation. And experimentation with treatment and control. Treatment is when you try to do the new thing. Control is where you are. You stay where you are, your current old technology. So control, you can think about it as null hypothesis H0 and treatment is its HA, alternate hypothesis. When you run an experiment that way, you can be assured that you are removing all the lurking variables. There would always be some sort of lurking variables, but when you run an experiment, due to randomization of how you sample, how you run a test, keeping everything else constant, you can be assured that you will get a result that is that can get you to a go, no-go decision. So, but remember, the tests, if they are not possible to run, then surveys are important way as well to keep in mind. But tests, experimentation is the best way to to get to a go, no-go decision, but to also get to a causality. So far we've all seen is correlation, but causality is an important aspect as well, and experimentation with tests allows us to do that causality link. So now let's take an example. Let's run a pilot study. So we asked the new turbine technology to manufacture 35 turbines. They manufactured 35 turbines, and then we find out that 12 of them are defective. So that is almost 34.3% defect rate. And so the second step for us is to choose our alpha. Alpha is the smallest significance value at which we would reject the null, right? So in this case, we say, hey, I want 5%. I just want it to be, the error shouldn't be more than 5%. The type 1 errors. I shouldn't be going to the new when I didn't need to. So 5% is your alpha. That's the second step. First step is define a null hypothesis. Second step is to run a trial experiment and then define an alpha. And so then you can calculate the z-score. So in this case, 0.4 is your null hypothesis. So and then you get 34.3. So it's 0.343 minus 0.4. And then we looked at this formula ahead. So this is nothing but x bar minus mu upon p. So p1 minus p hat by n, right? This is p hat. So when we do that, we can calculate the z-score. So the z-score here is minus 0.68. And then if we look this up at the z-table, we'll find out, we'll get the p-value. The p-value here is 0.25. So this basically says that alpha equals 5%. Can you reject that, hey, this value here is statistically significant to have a go, no-go decision? The answer is no, right? So you can only reject this at 25% confidence, but not at 5%. So when you run this experiment, you'll get a graph like this one, right? Where you can make type 1 or type 2 errors. So now let's assume that the reality is at 0.4, meaning 40% defect is we feel that is what the reality is. So the type 1 error happens here in this space, and let's assume this is 0.26, right? And we can calculate all of this based on this type 1 error 0.4. So this segment here, right, is basically saying what is the area. So let's say you want to say I want my type 1 errors to only happen max of 5%, right? So when you do that, you can calculate this 0.261, the decision point. So when you say my type 1 errors happens only 5%, you can calculate a decision point at which you can reject the null. So you get 0.26. So you don't keep your decision point at 0.4, even though you know that you can reject anything if you can less than 0.4 is good. You would actually go more aggressive, and the way you find out is through this 5% confidence. So you say, hey, 0.26 is my cutoff. This is where I decide. If I get a value less than 0.26, I adopt the new technology. If I get a value greater than 0.26, meaning greater than 26% of my parts are defective, then I don't adopt the new technology, right? So this is percentage parts defective divided by 100. So if it's 40%, then you get 0.4, and so on and so forth. So now, when do you make a type 1 error? Type 1 error happens when you get a sample that's here. Let's say it was 0.22, right? You ran a sample, and then you got 0.22, right? But in reality, it was 0.4. So your sample says, hey, the defect rate's really good for this new technology, 22%. But in reality, it's actually 0.4. So what do you do based on this sample? You make a decision to take the new technology. So this is an area that allows you to make type 1 errors. This is that area that allows you to make type 1 errors. Type 1 errors happen when your sample, in this case it was 34.3, but let's assume this was 22%. Then your sample would have said, hey, this is a good technology. So you would have gone through and adopted the new technology, but in reality you should not have. So you committed the error of type 1. So this is that area. Similarly, type 2 error. At 0.4, if you look at this, type 1 error happens here, so this is the same, type 1 error, and the complement of it is type 2. 95% chance that you're making a type 2 error at this 5%. So at any given point, imagine your company can be too aggressive to responding to customers' needs. In that case, you are most likely committing a type 1 error. Your numbers are way stricter. But if you're not really listening to your customers' needs, and they're complaining and that signal's not coming to you as an executive, you are committing a type 2 error, where you're failing to take an action. So in this case, what can happen? You decide you have a sample space and it says, hey, my defect rate is 0.22, but in reality, it is 0.4. The defect rate is much higher. But when you get 0.22, what do? You do nothing. So when you do nothing, you are committing type 2 errors. So type 2 errors is basically this whole area. This whole area, anytime a sample space comes in here and you make a decision of not doing anything, but in reality, it was supposed to be here, then you're making a type 2 error, right? So at 0.4, this becomes a complement. But imagine if the true reality was 0.3. Then for the same 5%, the type 2 error percentage reduces from 95% to 68%. And at the same decision point of 0.264, which is this one, then it's 50-50, type 1 and type 2 50-50. And then if you continue to become more and more aggressive, right? In this way, you're getting more aggressive as an employee. You are getting and taking much more care of your fixing bugs. You're taking care of the employees, the customer's requests. But you are committing less and less of type 1, but less and less of type 2, but you're committing more and more of type 1, meaning you're reacting too much, but your type 2 goes down. So either your type 1 goes down or your type 2 goes down, and this is completely dependent on business decision. you can at some point afford to not lose certain customers, and so you might have to go really deep with them to fix all of their issues, even at the cost of like type 1 errors. But at some point, when we fail to realize that there is a problem and we fail to act, that's a type 2 error. And so depending on what your balance is, you would have to constantly test out through various metrics as to where your organization stands. Are we committing a type 1 of acting too much and just wasting too much money? Or are we committing a type 2? I feel Apple. Think about it. Apple. What do you think Apple is committing? Are they committing type 1 error or are they committing type 2 error? Apple generates lots of cash, right? But what do they do with that? They just give it to their stockholders as dividends, and then they buy back shares. So they're not aggressive. So they definitely don't do type 1 errors, is what I feel. They're probably doing a lot of type 2 errors. They're just failing to take action when action was needed. Meaning they have lots of cash, they could be acquiring great companies. But they like to be in this type 2 space. They like to stay focused. They are very conservative. They're growing as well. They're a massive company. So Apple, I feel, falls here. Tesla. Let's think about Tesla. I think initially they were into type 1 errors. It's just taking too much. They bought too many things. Maybe Tesla is not a great example, but type 1 error is the company that just keeps buying companies, right? Keeps buying companies, and then they're like, we don't want to miss out on any of these opportunities, but they may not even be buying the right companies, right? They may be buying wrong investments. So type 1 error is where you're too aggressive, buying too many things. It's very important to run an experiment, understand the difference between where a type 1 error can happen, where a type 2 error can happen, and at where you are in the organization is very important. So in this case, we get a p-value of 0.25. That's not statistically significant. P-value of less than 0.05 is the norm, where you say, hey, I reject the null hypothesis. A low p-value is evidence against the null hypothesis, meaning low p-value supports to reject the null hypothesis. Small p-value is good. And power is nothing but 1 minus probability of type 2 error, right? So in this case, type 2 errors for us, if it was 68%, then we would say 1 minus 68%, so 32% is the power, right? So sometimes when you have a low power, you might not get significant p-value as well, so you might have to run that test for a longer period of time, or you might have to need more samples. So hopefully this was useful. With running the right statistical test, we can set up an experiment, we can get to a p-value, and then we can make a go no-go decision. And if we have a low p-value, that's evidence against the null. If we don't have a low p-value, in this case 0.25, it's not the evidence against the null, so you should not reject the null hypothesis and stay where you are, stay put. Think about Apple. And learn about type 1 and type 2 errors in detail is pretty critical in reflecting where you are in an organization. Are you committing too much of type 1? Are you committing too much of type 2? Or are you just right? So that's an important aspect of inference. 3 main things we learned so far: confidence interval, control limits, and now statistical tests with experimentation to get to causality eventually and decision making. Thanks.